Good day and welcome back to our third and final installment on vector valued functions. In previous videos, we've introduced some of the basic properties of vector valued functions, the idea that we represent them graphically as a space curve or a curve in three-dimensional space. And in the previous video, we sketched several common examples. What we are going to do now is explore some of the common questions that might be asked of us, specifically things involving finding a curve that might represent the intersection of two surfaces, or finding the point of intersection between a curve and a surface. So let's begin with this top example. Find a vector valued function that represents the curve of intersection of a cylinder and a plane. And the first thing I'm going to do is just draw a generic representation of this. So let's see here. We have a cylinder, x squared plus y squared equals 4. And I'm not trying to be overly specific, just kind of very generic. So it wraps around the z-axis, and it is a circle of radius 2 in any of the z equals traces. And then what we're doing is we are taking a plane and we are cutting this cylinder. And I don't need to draw the specific plane. I just need to get kind of a rough idea. So if I have a plane, I'm just going to draw a generic plane. I'm not 100% sure how much this would correspond to what we've indicated, but probably not all that well. But we have a cylinder, a plane, and visually we should now be able to see kind of how they intersect each other. It looks as though they would intersect in a curve much like the one drawn here. And kind of how I think of this visually is maybe this cylinder is representing kind of like say a paper towel cylinder or even a loaf of bread, and the plane is kind of a knife where we cut it, we take the top off, and then that portion that remains would be this curve of interest. Now, in order to sketch space curves, we said we had to exploit relationships between the individual parametric functions to come up with some surface that they lie on. Now, that same idea can be used, I'll say, kind of in reverse. So because the curve lies on the cylinder x squared plus y squared equals 4, this implies a relationship between the x and the y parametric functions. And we just need to know what is one example that would work for x and y, and then we'll see if we can kind of combine those together. And one possibility, something similar to what we talked about at the end of Calc 2, is you can come up with a parametric description of any circle of radius r just by letting x be r cosine and y being r sine. And here our radius is 2. And I do want to be very careful to note this is not the only choice. This would be one of many choices that would work. For example, you could switch around the x and the y coordinates. You could make x 2 cosine of 3t and y 2 sine of 3t. So there's many different possibilities. We just need one that works. And we now have the x and the y. So if we're thinking about working towards our vector valued function, we're throwing out that x could be 2 cosine and y could be 2 sine. But in order to complete this, what we need to do is determine z. And note we have two surfaces that we are working with, the cylinder and the plane. We've used what we can about the cylinder. We now need to use the plane. So looking at that equation of the plane, note that z is equal to 6 minus 2y. So writing down just precisely that equation of the plane and slightly regrouping the terms. And from above, if we say y is 2 sine of t, this would make z equal to 6 minus 4 sine t. And this would be a space curve that represents the curve of intersection of those two surfaces. And note I was very precise with my language to say it's A because this is a solution, not the only solution. So I know oftentimes in mathematics we might think we're looking for one in a very specific form of a solution. Here there's many choices. This is just one possibility. Okay, for our next example, I want to note that this is something that we've actually encountered previously in a slightly different context. So very generally speaking here, we want to know where does a curve intersect a surface. And that curve, it could be maybe say a line, and the surface could be, maybe say a plane. And on our worksheet dealing with lines and planes, we saw a very similar example. And I mentioned at that point in time it was a specific example of a more general type of problem. We are now to that more general type of problem. So let's see if we can draw a picture representing this. And note, I will always try to draw a picture. And on homeworks or exams, I may even ask you to draw the picture as well. So we have a helix, and we want to know where it intersects a sphere. And I don't have to be, overly specific. I just need to get a general idea. Maybe how many solutions do we expect to find? So if I have a sphere of radius root 2, centered at the origin, and then we also have a helix, and it's the helix that we encountered in our previous video. It's just wrapping around that z axis. So I'm going to draw something just very generic, and I have no idea if this is accurate or not, but let's say it's just wrapping around the z-axis. And we see that there should be 2 points of intersection. So disclaimer once again, the picture does not have to be perfect, far from it. Just get that generic general form across. So a helix intersecting a sphere. So the idea, and I'm going to write down the exact same thing that I had written down on a previous video, is to substitute the curve into the surface and solve. So let's go ahead and do that. If we take the parametric equations for this curve, x is cosine, y is sine, z is t. We now very clearly see that we can substitute those values into our surface and have an equation left over that only involves t. So x squared plus y squared plus z squared equals 2 becomes cosine squared plus sine squared plus t squared equals 2. And cosine squared plus sine squared, that's something we can work with. That's simply 1 by the Pythagorean identity. So t squared is equal to 1. And as advertised, we have 2 solutions corresponding to t equals 1 and t equals minus 1. And something I want to really emphasize is that we need to pay particular attention to the question that is asked. We want to find the points of intersection. Giving the parameter values and stopping at this point is a very common mistake, almost a mistake of omission, where everything is correct, you just haven't taken it far enough. So to find the points corresponding to a parameter value, we simply go back to our parametric equations and we substitute in. And the point corresponding to t equals 1 would be cosine 1, sine 1, 1. And for t equals minus 1, it would similarly be cosine minus 1, sine minus 1, and minus 1. And because cosine of 1 and sine of 1 are not common values, the best we can do in terms of exactness is leave it exactly in this form. So this completes our discussion of space curves and vector valued functions. In our next section, what we'll do is explore the calculus of vector value functions. So stay tuned and take care.